Hello everyone! This time let's make something a bit simpler so we can take a break from overly long videos. I will create an infinite tunnel using a so-called Menger sponge, which is a three-dimensional fractal that will project onto a two-dimensional plane. So let's get started. Like all fractals, this one will be generated purely through calculations, so we'll apply our shader to an empty color rect. I'll prepare the corresponding scene, so right-click in the scenes folder, create new scene. It is a user interface this time, and let's call it Menger Tunnel. OK, and right-click in the root node, add child node color rect. In the inspector, I'll change the color to black. Open layout, transform, and set the full HD resolution 1920 by 1080. OK. And scrolling down to the material section, creating a new shader material, click and adding a new shader type, shader mode canvas item. Name is mengertunnel.gd shader, and let's put it to the shaders folder. Create, and clicking again to open it in the shader editor. Okay, and as usual, I'll delete everything Godot generated using the template that we won't need for our purposes. That will leave us with only the fragment function, deleting vertex and deleting light. Ctrl S to save. Okay, let's start coding. Since we want the tunnel to appear square, regardless of the color rect dimensions, we'll need the dimensions of our current element, the color rect, to recalculate the aspect ratio. So I'll add the usual uniform parameter. Okay, let's put it to the top. Uniform vec2 resolution equals vec2, the default values 1920 and 1080. Okay, as you may have guessed, the 3D image generation will be done using array marching technology, which I've covered several times in the past and even made an entire video series about it. If you're interested in the details, I definitely recommend watching at least the first 2 episodes. This time, I'll just briefly remind you that this technique works by sending rays from the camera to every point on the screen, which the algorithm estimates the distance while the algorithm estimates the distance between such a ray origin and the surface of the object we want to display, which is described using a so-called SDF, which is signed distance field function. And that's exactly what we are going to do now. So we can imagine the Menger sponge as a cube from which we remove a three-dimensional cross, creating holes in all of its faces. This divides the cube into smaller parts, and in the next step we do the same thing to each of those parts, continuing the process until we achieve the desired result. Usually 3, at most 5 iterations are enough to see the difference in a normal rendering. So I'll add a parameter that defines the number of iterations. Uniform int iterations, and with a hint range, and the default value, as I said, 5 iterations should be enough. And let's make the range from 1 to, let's say, 10, and the step 1. I seriously doubt we would use 10 iterations, but let's keep it as it is. And now we can move on to the functions for calculating the surface of such an object. I say functions, plural, because for clarity I'll split the algorithm into several separate parts. So let's start with the most basic one, the definition of spatial cross, which looks like this. I will write first, then explain. Okay, and the name is float cross SDF. with the parameter vector 3, P, which is the point in the three-dimensional space. Alright, first let's fold the space. P is absolute value of P, and then vec3 D equals vec3 max P dot X, P dot Y. Then I will just copy and paste three times, and change the components. So here it would be P dot Y and P dot Z, and finally P dot X, P dot Z. All right, and let's return minimum of dx and minimum of dy dz minus 1/3. So it's simply 1 divided by 3. Okay, so what do we have here? The function returns the signed distance to a single infinite cross-shaped tube centered at the origin. Absolute value, as I said, folds space into the positive octant. By symmetry, the cross looks the same in all 8 directions. Then 3 pairwise max operations, this and this one, pick the so-called dominant 2 axes for each of 3 axis aligned tubes that form the cross shape. And finally, the minimum of these 3 values, dx, dy, and dz, selects whichever tube we are closest to. So it's the union of 3 tubes, and subtracting 1/3 sets the tube radius so the cross fits perfectly inside a unit cell. Okay, so now we have the basic cross, but by itself it's useless because it extends infinitely in all 3 directions. We'll need to repeat it in such a way that these crosses are placed next to each other at the spacing of a unit cube. So the following function will help us with that, and I'll call it float cross rep SDF for repetition. Alright, and again vec3 P is the input parameter, and here we simply do this vec3 Q equals modulo for repetition P plus 1 and modulo by 2 minus 1. So this assures the repetition in all 3 directions. And finally, let's return our cross as the f function applied on this new q point. Okay, so now we have the structure prepared for the first iteration. In the following iterations, we want to repeat this process, but on a smaller scale. So I'll add a simple function that will handle this scaling. So the next one is called float cross rep scale SDF vector 3 P, and now we need the scale factor, so float, let's call it S. Alright, and simply return cross rep SDF applied on this P times S, and the result is divided by S. Okay, and finally, we'll assemble the entire scene. In each iteration, we'll subtract crosses of the corresponding size from the whole space, eventually creating the characteristic hole-filled structure that we saw at the beginning of the video. So the function looks like this. Float, let's call it scene. And once again, vec3p, the input parameter, and now the calculation. So float scale starts at 1. Float this, the final distance to the object, it starts at 0. And finally, we will return the dist value. And now to calculate that. So the iterations in the cycle for int I from 0 to the parameter iterations I++. Okay, and now the calculation dist is max of dist and negative cross rep scale SDF P and scale. Okay, and let's recalculate the scale factor, which is multiplied by 3. Okay, and that's it. So what do we do here? We are making the max function of the negative value of this function, which simply means we are making a difference. This is exactly what I've been describing in the ray marching series I mentioned a while ago. Okay, and now we can move on to the fragment function, where we'll render the final object. First, I'll write the usual setup, shifting the coordinates origin to the center and recalculating the aspect ratio. So the fragment function, I'm deleting the comment, and now vec2 uv equals uv minus 0.5, shifting the origin to the center, and the aspect ratio uv.x is multiplied by resolution x divided by resolution y. Okay, I mentioned the camera that we'll use to project the 3D scene into 2D, so I'll define its position and direction. It will simply be placed at the origin and look straight ahead. So, vec3 camera pos is simply vec3 0, 0, 0. Okay, I could just use 1, 0 here, but later I'll change the third component to make it in motion. So let's keep it right now as it is, and vec3 camera there equals vec3 0, 0, 1, looking straight ahead, just into the screen. This camera is static for now. Later we'll animate it. And now we get to the ray marching itself. In the tutorials I mentioned earlier, I used the variables RO and RD for ray origin and ray direction, so I'll use them again this time. The ray origin corresponds to the camera position and will determine the direction from the UV coordinates of the current pixel, converting them into 3D by simply setting the third component to 0. So it's very simple. Vec3 RO is, as I said, camera position, camera pos, and vec3 RD equals camera there plus vec3 UV, and the third component is 0. Okay, and before I forget, we are only interested in the actual direction, so we'll need to normalize this vector. RD equals normalize of RD. Alright, for the following calculation to be useful, we'll need an accumulator for adding up intermediate results. I'll call it emission because in the end we'll use it for something resembling glow emission in a chosen color tone. Float emission starts at 0. So, ray marching. First, we'll determine the distance from the current origin to the object. Let's write it here. Float dist is our scene function applied on the ray origin. Alright, and now the algorithm itself, which consists of gradually shifting the ray origin and calculating new distances. Once we are close enough to the surface of the object, we'll consider it an intersection and terminate the loop. So we'll need two additional parameters, one to define the maximum number of such steps, and another for the surface distance that we consider an intersection. So I'm scrolling up to them to the uniform parameters section and writing them uniform int max steps with a hint range. And let's put it to 100 steps by default. And the range can be from, let's say, 50 to 1000, and the step is 1, of course. Okay, and the second one, uniform float surface dist with another hint range and the initial value 0.01. Let's make it very close. And from 0.1 to 0.01, I mean to 1 with the step 0.01. Okay, and we can now write the loop in which the ray marching will take place. To calculate the emission, I'll use an exponential with a negative exponent, which will give us a nice looking result, as you'll soon see. So scrolling down to the end of the fragment function and writing the loop for int I from 0 to max steps I++. Okay, and so as I said, if we are close enough to the semicolon, to the surface, we'll break the loop. So if dist is less than surface dist, and I think it was still too far away, so I'll divide it by 10. In this case, let's break the loop. Okay, and if not, we'll continue. So RO is increased by current RD times the dist value, and the new value of dist is again calculated from the scene function applied on the new RO vector, and we need to increase the emission. The result must be used somehow, so it's increased by, as I said, the exponent of dist times negative 0.4, for instance. Okay, and what's left is to render the pixel according to the resulting emission value. For that, I'll define two more parameters, color and brightness. So scrolling up again to the uniform parameter section and uniform vec4 color with the hint source color and the default value vec4. I think I use 0.3, 1, and 0.3 and 1 to give it some nice greenish shade, and we are using the RGBA format, hence vector 4. And as we know, source color hint simply adds the color picker to the inspector. And the second one, as I said, is brightness, uniform float brightness with a hint range, and default brightness I set 2.5, and the range from 0 to 1 with the step 0.01. Okay, and I think we can assign the result to the output variable color. So once again, scrolling down to the end of the fragment function, and I'll write the final line, color equals color times emission times brightness, and I think times 0.1 to give it some better look. Wait for it. Okay, not a bad effect. What do you think? I would say the host created by subtracking. The spatial crosses are clearly visible. And all that's left is to set this tunnel in motion. So I'll add one final parameter for speed. So for the last time, scrolling up to the uniform parameter section and uniform float speed with a hint range, and the initial speed I think I set to 0.5 again, and let's make it from 0 to, for instance, 4 with the step 0.01, and let's scroll down to the fragment function, and this time I'll find the camera pose definition and replace the last component with time times speed, and it should go now. Perfect, we are done. We have another tunnel in our collection, and now we can try changing some of the parameters. So I will find them in the inspector, expanding shader parameters, and for instance, let's decrease the number of iterations for 3. Can you observe how it changes? 2 or just 1? Let's get back to 5, and we can see that if I increase more, it's barely visible, maybe not at all. Okay, and the color, yeah, I think it's clear. There's no need to change it right now. We can change the brightness, brighter, darker, and of course speed, faster, or completely stopped. Okay, and I think this is definitely everything I wanted to show today. Thank you very much for watching. We could certainly improve a tunnel like this in many ways. For example, by giving it a slow rotation, changing the colors based on the distance from the camera, or deforming its square shape. But as usual, I'll leave these details up to each programmer to experiment with on their own. For now, take care, good luck with your game projects, and I'll see you in the next video.